power. Third. And then plus, we have a 3 there, but I got to take the antiderivative of t to the first power, which is 1/2 t squared. So this will be 3/2 t squared. And then plus ct, and then plus d. Hey, have I ever mentioned to you, I don't think I have because I don't use t very often here, but do y'all see how I curl my t's? I didn't always curl my t's, but I realized that my pluses and t's started to look the same sometimes.
Yeah, you've mentioned that.
Okay, so curling your t's might be something that you adopt if you're going to do a lot of math, because t does come up quite a bit later on. You see what I'm saying, right? Like without that curl, they look a lot like the same thing.
C++.
C++, yes. All right, so there we go. Now, am I going to be able to nail down D? And I'm going to have to nail down C also. Well, I'm given some information here, right? S of 1 is 4. Let's use that. Okay? So using the fact that S of 1 is 4, it means when I plug 1 into this, I should get 4, shouldn't I? So let's plug 1 in. Let's plug 1 in for t. So 1/12 times 1 to the 4th power minus 1/6 times 1 to the 3rd power plus 3/2 times 1 squared plus c times 1 plus d. That must equal 4. Yeah, that's life. Okay. All right, so 1/12 minus a 1/6 plus 3/2 plus c plus d equals 4. Here's what I'm going to do. I would like to put all these numbers together, right? And like, I don't know, just put it all together. But I'm going to clear the fractions out. I'm just going to get rid of fractions. So to do that, I'm going to get a common denominator, which is 12. I'm going to multiply every single thing I see by 12, both sides of the equation. All right? That'll get rid of fractions, won't it? And I'm allowed to do that because I have an equation. So if I multiply this by 12, what do I get? 1. If I multiply this by 12, I'm going to get 2, right? So minus 2. Multiply this by 12. 3/2 times 12 over 1. This cancels, you get 6. So 3 times 6 is 18. So this is 18. Y'all know what I'm doing here? Yes. Plus 12c plus 12d, d equals 48. And to me, it's just easier to work with the numbers like this. So put these together. This is going to be 17 over here, right? And then I'm going to subtract 17 on both sides. So I'm going to get 12c plus 12d equals 31. Okay. Well, that still sucks because I have one equation, I have two unknowns, don't I? I can't solve for c right now because I don't know d. I can't solve for d because I don't know c. But I've only used one piece of information, right? I have another piece of information. S of 4 is 3, right? So if I do that and I plug in 4 into this, I'm going to get another equation. And I'm going to have two equations with two unknowns, and that's a system of equations. Okay, so now using, using S of, you know what, can we change this to 2 just to make our lives a little easier? Let's just make that S of 2 is 3, just to make our lives a little bit simpler. So S of 2 is 3 means that when I plug 2 into here, right? So 1/12 times 2 to the 4th minus 1/6 times 2 cubed plus 3/2 times 2 squared plus c times 2, which is 2c, plus d equals 3. It's still going to suck, but I think the numbers were just a little easier to work with that 2 being replaced, or that 4 being replaced by 2. What's 2 to the 4th? 16? So I have 16 twelfths minus 4 sixths, oh no, 8 sixths. I could reduce those, but I'm not right now, okay? What does this become? This is like 4, and then you could divide that by 2, couldn't you? So I think that's just going to come out to be a 6 there. You okay with that? Can I multiply by 12 again, just to get rid of fractions? If you'd like to work with the fractions, you can. I'm just going to clear them out, though. Is that all right with you? Mm-hmm. Okay, so if I multiply this by 12, I get 16. I multiply this by 12, I get... Are those the same thing? Yeah. Right? Yeah, if I multiply this by 12, I get 16. They're going to cancel. Okay, plus, let's see, 12 times 6. What? 72, that's right, yeah, 72, sorry. And then 24C, and then 12D, and then 36. So these 16s cancel. And I'm going to subtract 72 on both sides. And I have a negative, but let's see, I have 24C plus 12D equals negative 36. Questions? So I have another equation with 2 unknowns, but I already had an equation with 2 unknowns. So if I put these together, 12C plus 12D equals 31, then I have a system of equations, which you can solve either using elimination or substitution, and that would be up to you. How would you solve that? Elimination? I'd use elimination also, because those 12Ds are ready to go away, aren't they? So you would have to multiply either the top row or the bottom row by -1. I'm going to multiply the top row by -1. I said I'm doing elimination right now, right? If you don't have any idea what I'm doing, then I would go look up elimination, system of equations, solving system of equations with elimination. Google it. Do whatever you need to do. So multiply the top row by -1, and now I add straight down. The whole goal of multiplying by -1 was to get these 12Ds to cancel. So add down, get negative 12C. I'm going to add there. These go away, and then that equals 67. And if I divide both sides by -12, I'm going to find what C is. So C is 67 over -12. So I've nailed down what C is, right? How do you get D? Plug C into any of these, into either one of these. You think you could do that on your own? Yeah? Okay. So your final answer will be this right here, with C replaced with negative 67 over 12, and then D replaced with whatever you get when you solve for D. And that would be your function. Oh, no, I'm going to have to get it, aren't I? Because I haven't answered the question. I asked for S of 10, didn't I? So what I would need to do is I need to get the C in here and get the D in here, right? That would be my function. And then I need to plug 10 in. Plug 10 into this, and that would give me my answer. I won't do it. I'll let you do it. You understand what you need to do? Solve for D. Once you get D, there's your function, then plug 10 in, that's your answer. Okay. I think that's good. So this is 4.7. I would expect that you would do your homework from this section, 4.7. Now, let's talk about why we need antiderivatives for anything. All right, we're going to get a little historical here now. And I'm not here to argue about personal beliefs and where we came from and how we got here and everything like all that stuff. But
Jesus made us 6,000 years ago. I don't want to argue about this.
we're not talking about it anymore. Okay, so look. There was a point in time where I hope we would all agree that we started to say this shit's my shit, this is my land, you stay off my land, right? Do we all agree with that? We have borders between one another. At some point, that wasn't an issue. Maybe at some point it wasn't an issue. Who knows?
We never know.
I don't know. Maybe there was a point in time where we all got along and it didn't matter.
Yeah, right.
Okay? But we obviously live in a time now where it matters, right? Like you have your land and whatever you live, that's yours or whatever. So there was a point in time where you had people and they started to break up the land, right? So let's see. The United States. There we go. Okay, so Louisiana Purchase. We started partitioning up this land, right? And even our states are broken up into borders and stuff like that. Well, when we did that, we had to have an accurate way of measuring how much stuff you have versus mine is in terms of the area of the land. And so we could all agree, I guess, that if our land was rectangular, we would have length and width, and then the area would just be length times width, and we're done, right? Unfortunately, it's not always rectangular, right? So we need to be able to measure some more complicated shapes, areas of more complicated shapes. So maybe something that's like a triangle came into play. So what's the area of this? So, we discovered, well, if you can figure out the height and the base, then the area is going to be 1/2 base times height, and we're all good still. As long as your land is rectangular or triangular, we're good, right? And then we started to get things that maybe looked more like this. Yeah. That's not Texas. That's just something else, right? So we have to find the area of this. So could we find the area of this? It's not a rectangle, it's not a triangle. But would we feel confident that we could figure out what the area of this is? You could just draw a bunch of triangles, right? You could maybe say, all right, I'm going to connect there to there and there to there, and you've got triangle 1, 2, and 3, and just find the area of those 3 triangles, and we're done, right? When does it start becoming an issue? When you're in Texas, yes. No.
When you start getting into inconsistent shapes along the lines and the outer edge, you don't have any linear lengths.
Okay.
You have lines that are broken up into segments that are oscillating and going back and forth.
Okay, so just not lines, right? All of these shapes have lines, straight lines, right? But if a river runs along your property line, that river's not going to be a straight line. So we have to have ways of measuring a shape like, I don't know, maybe you Maybe your land is pretty rectangular, but that river cuts through it. So the river cuts through like this, right? Something like that. So we're trying to find the area of that. Now you could try a triangle. You could say, look, there's a triangle right there, right? But that's not exactly right because that curves. It's not a straight line. So this was a major problem. How do you find the areas of things that are not straight line segments like this? Well, one of the first ones that we went after, when I say we, I'm talking about humans, right? Okay. One of the first shapes we went after was the circle. And we said, okay, can we find the area of that? Yeah, they just opened up a book and it said pi r squared, right? No. How did they come up with pi r squared?
They use string.
They were what?
That's how the Mayans did it. The Mayans figured out the string root to solve the length of pi.
I'm saying, where did this come from? Different civilizations came up with ways to approximate pi. They used approximations. Sometimes they were fractions. 22/7 is an approximation. If you take 22 and divide it by 7, what do you get? 3.14 what? 28. Okay, pi is actually 3.1415, and it keeps going. But you can see that 22/7 is pretty close, right? And if we're talking about the Chinese did this thousands of years ago, that's good enough for what they needed to do. And the Mayans did something similar where they had a number that they could use that was good enough. But the exact area of a circle came later. Okay, the formula here came later. So where did it come from? How did it arrive at? In my Cal 2 class that I teach, I think I show them 2 or 3 different ways to get this formula.
Show us one.
In polar, well maybe
Oh yeah, in polar.
in polar, and then you can do it in Cartesian with trig sub, yeah. All right, so the thing is, this was a problem, right? We couldn't figure out how to find the area of a circle. So what the Chinese did, okay, they were the first ones to do this and come up with this method. Okay, they came up with this thing called, so does everyone understand this is the big question, right? Like, how do we arrive at something like this? All these other shapes were good. So the way that they did it is they would get a piece of paper out and they would draw a very, very good circle with, like a compass almost, right? But they just put a pin with a string and then draw a circle, very precise. And then what they would do is they would come in here, and I'll do this in blue. They would draw like a square or something inside the circle. And they would measure the area of that. And the area of that blue square would be too small, right? So then they would come in and they would fill in this gap right here with the rectangle. And this gap here with the rectangle, this gap with the rectangle, and this gap with the rectangle. And they would add up all those little rectangle areas. And that area would still be too small, right? So they would draw even smaller little rectangles in here and try and fill in as many gaps as they could, measuring out these little tiny things. And they would sum all these up, right? So they would take a sum of all these rectangles. And that area that they got would be too small, right? So the area that they get when they add these up, I'm going to call it area. I'm going to put too small. Okay, that's just to remind you that came from adding up these rectangles inside, okay? That area is obviously smaller than the true area, right? The true area is bigger than that. Yeah? So then what they would do is they would take that same circle and they would draw a square around it. And they would find the area of this square. What's the area of that square? Well, who knows, right? But it's bigger. It's bigger than the true area, isn't it? And then what they would do is draw little rectangles in here and start subtracting those from the big square. So you got this big square that's too much. You start taking away these little chunks, but that's still, even when you take away those little chunks, it's still too much, isn't it? So what they get over here is something that is too big. And well, they just got better and better at drawing smaller and smaller rectangles, and they started to smash the true area between two numbers. Right? So they would get better at the inside measurements, better at the outside, and they started to realize that the true area of that circle had to be between two numbers. They just kind of like squeezed it down as best they could. And 22/7 appeared to be the magic number for them. Does that make sense? All right. Now, that's not acceptable in terms of the way it's approached now, but this idea is important. This is called the method, I'm not making this up, of exhaustion. The method of exhaustion. Because it's tedious, it's exhausting to do something like that, right? But the idea here is fundamental to what I'm trying to point out today. And that's what the Chinese really wanted to do was to try and put an infinite number of rectangles in here, right? In that blue, they wanted an infinite number of rectangles, but they couldn't do an infinite number of computations because you don't have enough time. And you can't draw tiny little rectangles that are maybe smaller than the width of your writing instrument, right? So they hit some barrier in terms of what they could physically do. But the idea was an infinite number of rectangles that seemed to somehow get smaller and smaller. Does that make sense? Now, calculus came along, and calculus allows us to do things that become infinite. Limits, right? Let something go to infinity. Let something go to infinity. And that's what Newton was able to do, is to get to an area, we are going to do something similar to this. But we will apply a limit at the end, and that limit will give us the true area. It's pretty remarkable. All right, that's kind of a historical perspective on why areas became necessary, and now let's see how we could come up with a similar attack to a problem. And use a limit and all that stuff. Okay, so let me put the task, the problem at hand here. I want us to find the area under the function f of x equals x squared plus 1 on the interval 0, 2. I'm going to draw the picture, all right? X squared plus 1 is this parabola, right? If we look at the interval 0 to 2, imagine going up here. Wouldn't that take you to 5? Wouldn't that be 5 up there? Yes? If we look at the region below this graph, it's similar to that picture I showed you with the land with the river running through it, right? What is the area of this? That's what we want to know. Does everyone get it? All right, so here's what I could do. See if you agree with this or not. I need to kind of zoom in on this picture. I need to really zoom in on it. Using a similar approach that the Chinese used, I could approximate this area by, don't write this down, but just watch me. I could say, okay, I'm going to take a rectangle that goes around this thing, like this, and find the area of that red rectangle, right? And what would the area of that red rectangle be, by the way? 2, it's 2 times 5, right? That's 10, right? So if I do one rectangle, the area is 10, and that's obviously too big.
Wouldn't it technically be bigger than 10?
Why?
Because it's going around.
What's going around?
He's being,
Oh yeah, okay, yes. I see, because I was not exactly on the edge. Okay, yes. Okay, so that approximation sucks, doesn't it? Everything in here is not supposed to be in that 10, right? Okay, so how about this instead? What if instead of doing one rectangle, I do 2 of them? So watch this. I'm going to go and instead of going all the way across like I did, I'm going to go halfway first. So I'm going to go only from 1 to 2. And then when I get to 1, I'm going to plug 1 into the function. And what happens when I plug 1 into the function? I get 2. Now my picture sucks, but I would go up, right, like this, and it would spit out 2, wouldn't it? And I have that rectangle. And then my second rectangle, I'm going to go from 1 to 2 and go all the way up and then over and down, like that. Do you agree that that would be better than my first approximation? What would it be? Well, let's see. This is 1 wide now, right? 1 times 2 is 2. So I'm going to get that the area is equal to 2 plus this one. 1 times 5, so 5 is 7. Agree? It's still too much, though, because this right here was too much and that was too much. So what would be even better?
Making more rectangles.
3 rectangles, right? 4 rectangles, 5 rectangles, 10 rectangles, 1,000 rectangles, an infinite number of rectangles would be perfect, wouldn't it? Okay, so let me do 4, because 4 will be easy to cut. 4 rectangles. Let's talk about the area. So watch what happens. What I want you to really see here is how this picture keeps changing. When I do 4 rectangles, I'm going to cut this interval into 4 equal segments. I'm going to go a quarter of the way, because I'm doing 4 rectangles. I'm going to go up and then over, right? The next one I'm going to go up and then over. Next one up and then over and then up and then over. And do you agree that that area is still too big, but better than this? Yes? Can we figure out what this is? How wide are each of these?
those are halves.
These are all halves. How are you getting that?
I can see that they're halves.
How?
Well, half of one.
Yeah, I mean, so, but it's really this distance, right, which is 2, divided by how many rectangles you have, which is 4. Yes? Okay. So these are each a half. So if that's a half, what is this point? What is this x-coordinate right here? A half, right? This is a half wide is what I'm saying. But that is the actual x-coordinate 1/2. Why is that important? Because that gets plugged into the function. That gets plugged in. And so this height right here, isn't that f of a half? Which turns out to be 1/4 plus 1, which is 5/4. But I'm trying to get you to see a pattern right now. This next rectangle is still a half wide. Okay? But that right there, that x-coordinate is 1, right? But isn't that just 2 of the halves? Follow me. Just follow me, all right? This is 1/2, but to get to this x-coordinate, I have to go 2 halves. All right? And then I plug this in, and this value that would come out up here would be f of 1, right? Which would be the 2 times a half. I know that seems stupid, but again, we're trying to follow a pattern here. This one would be what? 3 halves? Which means I took 3 of those halves, right, to get to that. Then I plug that in up here, and it spits out f of the 3 times the half, whatever that number becomes, right? And then the last one is 4 halves, which is 2. And I plug that in, and I get this value out here, f of 4 times a half. Make sense? So if I wanted to know the area of 4 rectangles, what I'm doing is this. I am taking the width of each rectangle, right, which is, you said the width of each one was a half? But wasn't that 2 minus 0 over 4? Wasn't that the distance from here to here, which is 2 minus 0? Right, it's this x-coordinate minus this x-coordinate. That's how the distance between them, divided by how many rectangles I had. So do you all agree that's how wide each rectangle is? Times f evaluated at the first mark, this one right here. So f of a half. Yes, so far? Plus now the width of the rectangle again. Times f of 2 times a half. Plus the width of the rectangle again. F of, now I'm at the third half, right? Plus the width last time, f of 4 times a half. And if I added all those up, I would get the next good approximation, yeah? You sure you're all right with that? No? It's okay. I just want to see that you're just generally following. Generally following?
Yeah.
Okay.
I got it.
Okay, so here's my next very profound question for you. What if I wanted to cut this into n rectangles? N rectangles. See if we can't do this. I don't know, I feel like I might be pushing too hard here, but I'm going to go for it. Okay, if I did n rectangles, the area would be the width of each rectangle. So how wide would each rectangle be? Nope.
2 minus 0 over
So it's the width of the whole thing, which was 2 minus 0, over n. That's what I was trying to get you to see here. Like, yes, I understand that that's 1/2, but it's more profound if you understand that it's actually the length of the interval over how many rectangles you had. So the area should be the length of the interval, 2 minus 1 over n, right? Times f evaluated at, now this is where it gets really tricky. I was first evaluating at 1 times that first jump, right? Which was a half. And then I had 2 of those jumps, then 3 of those jumps, then 4 of those jumps, and I kept going, right? Stopping at 4. So I should have, first of all, 1 of those jumps. What's my first jump? Well, it was 1/2 here because they were each 1/2 wide. How wide are each of these? 2 minus 0 over n again, right? Isn't it?
Yes.
This 1/2 was actually 2 minus 0 over n. 2 minus 0 over 4 in this case. So this is one of those 2 minus 0 over n's. Then plus another width of a rectangle, 2 minus 0 over n times f of 2 of those 2 minus 0 over n's. Then plus, same thing, right? 2 minus 0 over n times f of 3 of those, right? And I keep doing that until I get to the very last one, which would be 2 minus 0 over n times f of n, because I'm stopping at n this time, n of those 2 minus 0 over n's. Okay, that would be the sum that I would have to do if I wanted to figure out the area with n rectangles. Yeah? Okay, that is known as a Riemann sum, named after the mathematician who developed this idea of It's called Riemann sums. Wow, it's kind of crazy, isn't it? Now there are some things in that problem that I want you to recognize. Every single one of those has a 2 minus 0 over n, right? 2 minus 0 over n, every single one. So I could do this. I'm just going to change 2 minus 0 over n to 2 over n because it's going to save me some time. Since they all have the 2 minus 0 over n in them, I factored it out and I just slapped it to the back. Okay? This is just going to multiply times that. Now, I'm at a point where I'm running out of time. I'm going to have to continue this, but. This becomes very hard to do, especially if I want the number of rectangles to go to infinity, right? If I want the number of rectangles to go to infinity, then how do you do it? It's like an infinite sum, isn't it? Well, check this out. This is kind of mind-blowing. What's the antiderivative of that function? What's the antiderivative of that function? 1/3 x cubed plus x plus c. Right? Now somehow, some way, like, okay, great, that's there, right? But what's the use of it? Here's what I'd like for us to do now. Plug 2 into this, and then plug 0 into this. Now when I say 2 and 0, those were our two endpoints, weren't they? 0 and 2? So if I plug 2 into this, what do I get? 8/3 plus 2 plus c. And if you plug in 0 in here, what do you get? C. Now what I'd like for you to do is subtract those two answers. And if you subtract them, the c's will cancel. You'll get 8/3 plus 2, which is 14/3. 14/3, which is, I think it's 14/3. 3 on top, yeah, 14/3, which is approximately 4.666 forever, I think. Yes? 4.666, yes? Guess what this is? This is the devil's number, yes. Guess what this is? This is the area under the curve. That's what it is. See this thing over here? You know how we had approximated it? Bad approximation was 10.
Yeah.
Then we did 2 rectangles and it was 7. I said if we did 4 rectangles, it would be better. And if we could do this calculation, if we could do it infinitely many times, we would get an answer. Well, guess what? The antiderivative evaluated at the 2 endpoints does it all for you. And it's unbelievable that it does it, but it does it. So this right here is the true area under that curve. All right, so next class I'll actually introduce you to new notation, and I hope that you'll see with the notation how it connects to this. But y'all have a good weekend. Do your homework for 4-7.
Wrapping up the day.
Yeah.
At the end, when you said you could find C, I realized you could show us the derivative was going to show you the desired area.
That's the area.
The next